Good evening. I'm Tudor, CEO of Harmonic.
And I'm Vlad, Executive Chairman of Harmonic. We are here live from the HP garage in Palo Alto, long considered the birthplace of Silicon Valley. So it's pretty amazing that they let us live stream from here. So today we find ourselves yet again at an important inflection point, and we can draw a line from the past, sometimes modest beginnings of our industry, when Bill and Dave were building products right here in this garage by themselves, all the way to the exciting and sometimes nerve-wracking future. Now we're here to talk about artificial intelligence, more specifically, mathematical superintelligence.
And mathematical superintelligence is artificial intelligence that can solve math problems at a greater capability than all humans. And it's getting closer by the day. But before we get into it, we want to start by celebrating some amazing human mathematicians. As you may know, the International Mathematical Olympiad, the most prestigious mathematics competition in the world, recently finished in Australia.
And these 5 amazing high schoolers who you see up here all achieved perfect scores of 42 out of 42, a feat that no AI has matched thus far. Ivan Chaskovic, Warren Bay, Leon Deng, Hengyi Zhang, and Satoshi Kano.
And how did you do on the IMO, Vlad?
Would it shock you to hear that I didn't even qualify for the IMO? No, I tapped out at Amy level, which is 2 rungs below even being allowed to sit for the IMO. And even with that, I still became a pure maths PhD student and started some companies. So that's how challenging this competition is. How about you?
Well, same. But what about your home country of Bulgaria? How'd they do this year?
Not bad, actually. And shout out to Angel Christov, representing the great country of Bulgaria with 34 points. Just 1 little point shy of gold, just missed it by a hair.
Well, I know you're going to ask about Romania, where Pavel Ciurea and Emanuel Mazăre both got 35 points and brought home the gold for Romania.
I wasn't going to ask, but thank you for telling me anyway. And congrats to your Romanian countrymen. They're probably celebrating right now down on the Bulgarian Black Sea coast.
I'm sure they are, but why don't we stop bragging about our home countries and get into why we're here?
Okay, yes, sure. So about 1 year ago, we unveiled our first AI mathematics model, Aristotle. And at that time, we benchmarked Aristotle on Mini F to F, which is the leading formal mathematics benchmark. And it scored 90%. Now, Tudor, how did you feel when we got that result?
I felt pretty good. That was a state-of-the-art result at the time, but I should clarify that the 90% was using computer algebra tools in addition to formal verification. A few months ago, after quite a bit of training after the first run, we ran again on the benchmark and basically closed it off with no computer algebra.
No computer algebra. It did it by itself. And you called that a YOLO run, did you not?
It was a YOLO run. And as a result, we've now turned our attention to more challenging benchmarks.
Which is where the IMO comes in.
The IMO is unique because it's not only a difficult math benchmark, but also the problems each year are ones that haven't been seen before. And that actually makes it a perfect test of frontier math reasoning capabilities for different AI models.
Before we get into the results, let's first discuss why we even care about mathematics, because it's not just so that we can help you do well on your SATs, although that's a very nice side effect. We believe that mathematics is the foundation of all human knowledge. And I should actually point out that there is some debate about this. Some believe physics is more fundamental than mathematics because it's tied to the real world. Others say philosophy, since it actually deals with the foundations of knowledge and reason. What do you think, Tudor?
I think math takes the crown still.
I agree with you. And actually, when I started my freshman year at Stanford, I intended to double major in physics and philosophy, 2 of these disciplines that some argue are the most fundamental. But I found their explanations for some things to be very unrigorous, to put it mildly. So I started asking a lot of questions, and they sent me over to the math department. You see, modern theoretical physics is entirely dependent on the mathematical fields of real and complex analysis and differential geometry. Modern philosophy is built on top of set theory and first-order logic. And these are actually precisely the fields of mathematics where our AI model Aristotle does exceptionally well. And so by accelerating progress in mathematics, we actually accelerate progress in all dependent disciplines that lie downstream, including physics, philosophy, computer science, and even engineering. So we believe that building mathematical superintelligence can not only help us answer the big questions, like what happened before the Big Bang, but can also accelerate the development of new technologies, both hardware and software.
I mean, that sounds completely amazing, but I think there's just one problem.
Oh no, what is it?
Well, as AI starts discovering more and more math, it's actually going to be really hard for people to keep up. Verification takes a long time and becomes a huge bottleneck. For example, in 1993, a mathematician named Andrew Wiles submitted a proof of Fermat's last theorem, which is one of the greatest problems in mathematics, unsolved for about 400 years. Wiles first announced the proof in 1993, and then an error was found several months later. He spent a year fixing it, and the proof was ultimately resubmitted and accepted in mid-1995, a full 2 years after the initial submission.
One of my colleagues was a former math professor at MIT, and he told me he spends over half his time checking his grad students' proofs.
And more recently, Grigori Perelman proved the Poincare conjecture, which took about 4 years for the proof to be fully verified and accepted.
Very similar examples in scale
Exactly.
and magnitude, right? But as mathematical superintelligence discovers math of this magnitude every week instead of every decade, it becomes impossible for humans to keep up with checking it all. And this creates the verification problem.
But we've got a solution in mind, and this involves making use of what's called formal verification. Formal verification is translating math proofs to computer code and checking that every statement, and consequently the entire proof itself, follows logically from the basic axioms of math.
So humans no longer have to do manual verification. It's done automatically, and that's an amazing benefit.
And it turned out this worked amazingly well for us at this year's IMO, where we're very proud to announce that our AI model, Aristotle, achieved gold medal level performance, solving 5 problems, and critically, didn't require any human mathematicians to manually verify its solutions.
No human verification. That's an incredible accomplishment. So why don't we get right into the results? I'd like to welcome up Aidan Swope, one of Harmonic's AI researchers, also our first employee.
Hello, Aidan.
Hey.
Let me make some room. Why don't you take my chair? And actually, while he's getting the system up, I'm going to be scanning X for questions. And at the end, maybe I'll moderate some Q&A. What do you guys think? So please ask hard-hitting questions as we go along. And we'll do our best to give mediocre answers.
Oh, I didn't know I had to answer live Q&A.
Mediocre, unscripted answers. So
Right.
Hopefully expectations are managed appropriately.
Great. So I'm excited to talk about the 5 problems that we solved at this year's IMO. Again, we proved them all formally, and we used a programming language called Lean for this. Lean's a very popular programming language for formal verification of math problems. I figured I would mention just a little bit about how Lean works before we get into the problems and solutions. So this is what the statement of a problem looks like in Lean. You'll notice that it says "by sorry," and it's a very short file, so it doesn't include the proof. This is everything that we provide to the model. It looks at the sort of English description of the statement and then the formal description of the statement. And in this case, we're basically proving that this sort of set of numbers, 0, 1, and 3, is exactly equal to some set that we're looking for. By contrast, the full proof is really long. So I'll be talking about just kind of highlights, but we'll be releasing these proofs, but I won't be going through line by line at this time.
Thank you.
Are you sure?
Yeah. So for problem 1, we're looking at lines in the plane, and there's some condition on these lines where they can be called sunny if they're not parallel to either axis or the negative diagonal. And we're trying to sort of count the number of, we're trying to determine all numbers such that there could exist n lines that have these properties. Again, I won't go into too much depth in the proof. But something that's important to remember about these kinds of problems is that they're very visual, actually. There were a lot of sort of combinatoric style problems at this year's IMO, and something that's difficult about visual problems is that there are certain things that are obvious to people that are not at all obvious formally. So, talking about like whether a point lies on a line, something like that, that you can just see by eye may take, 100 lines of Lean code to actually verify that it's absolutely true.
Or understanding the floor tilings at the Sunshine Coast Airport.
Right. We'll get to that. So, like I said, this is everything that's provided to the model, and the model produced this, 1,000-some line Lean proof. But what I think is the most interesting thing is that not only does the model produce a proof, but it also produces English comments explaining exactly what it's doing. So for some kind of more obvious steps, like just a case analysis, the model doesn't need to explain it, but whenever there's something more non-trivial, it sort of thinks out loud. I think that proofs have value not only in telling you what's true or false, but also in teaching you things about math. And I think this is a very sort of compelling interface to that, where you know it's true, but then you can also see why. Not only that, when the proof involves some kind of auxiliary definitions or objects, the model generates those too. Maybe one kind of fun fact about this proof is that it's different than the proofs that people are talking about in the forums and that we think are going to be in the solution guide. Those are kind of based on like a geometric sort of covering argument, whereas our model proves that the lines form what's called a derangement.
A derangement?
Yes, I actually hadn't heard of a derangement before I looked at this proof. It's a funny kind of permutation where you're assured that no point in the output sort of stays in the same place it was in the input. So, without talking too much more about this one, maybe let's look at problem 2, which is geometry. Tudor, would you like to explain that one?
Sounds great. Do you want to pull it up?
Yes.
So this is a planar geometry problem, and it's actually the first IMO problem that our system was able to solve. Funny enough, it solved it instantly and recognized what it had to do. The great thing about geometry is that I can actually walk you through with nice pictures instead of code. So first, let's talk about what we're trying to prove. In this animation, we're going to see the problem setup and the steps. And if we go forward a couple frames, we're going to see the circle that goes through the points B, E, F. So this is an important circle because in the next frame, when we draw the line through H that's parallel through AP, we want to prove that this line is tangent to the circle BEF that we saw in the previous frame. Now, if you zoom out and look at this image, just pausing for a second, you'll see that it maybe feels a little bit unbalanced. We've got a circle on the left and a big hole on the right. And it turns out that recognizing this asymmetry actually was Aristotle's key insight. Its flash of brilliance was in drawing the circle through DEF with center point W that's highlighted in blue and kind of balances out a little bit. And as we go forward, each frame of the animation will cover a different deduction step. And the steps are almost like a perfectly choreographed dance, alternating between identifying equal ratios based on triangle similarity and equal angles, and vice versa. And the system also uses a technique called angle chasing, which human competitors use to reason about equal angles across disparate parts of the diagram. So for example, in this step, we see the first use of the triangle EOX, which is directly relevant for the goal. And if we keep going, near the end of the proof, we're going to find our first non-trivial equal ratio statement, which indicates that the ratio of segments on one side of a triangle is equal to the ratio of two sides of the triangle BEF. And the important thing here is to remember that triangle BEF is also part of the circle that we want to show tangency to. And if we finish up the proof with just a few more steps, we've proved that BO has the same length as BX, and with that we're done.
That's really cool.
And I'll give it back to you for Q3.
Great. So Q3 was another combinatorics problem. This one, we're talking about functions that are said to be bonza. Again, it's Australia, so I learned a bunch of cool new words. Apparently, bonza means it's really cool or excellent in surfer slang.
Tubular.
Right. So we're saying a function is tubular if f of a divides b to the a minus f of b to the f of a.
Tubular is also a mathematical term, though, isn't it?
Oh, really? I didn't know that, actually. So, like the previous one, there's a whole bunch of interesting stuff that I'm going to skip. But here's the human provided statement of the theorem, pretty concise. And here's our model's output. It's actually not nearly as long as the last one. This problem is the fastest solve besides the pure geometry solve, if you go by wall clock time for our system. But it relies on something that I alluded to before, but I think is really important, which is that our model not only does kind of deductive reasoning, but can also construct these objects from the infinitely many objects that you could define. So sort of the key insight in this problem is it comes at the very beginning, and it's defining this set S. You say, for any bonza function f, let S be the set of prime numbers for which f of p is greater than 1. it's kind of a weird notion, actually. It's certainly not the first thing that I would think of. And it sort of demonstrates that the model doesn't just like generate this file from front to back like a chat model would. It actually makes multiple passes at the problem. Sometimes it fails completely, sometimes it makes partial progress, but it learns a little bit each time. And on the pass that finally got it, it seems like it learned that this kind of construction made a lot of headway in talking about characterizing Bonza functions.
I mean, that's amazing. Should we go on to Q4?
Let's do it. Vlad, this one's number theory. Would you like to talk about it?
Yeah, well, thank you. It would be an honor, actually, gentlemen. This is an elementary number theory problem, Q4. So you've got it up, I see. By the way, shout out to my number theory professor, Kanan Soundararajan from Stanford. I would skip that class so often that the professor one time gave my buddy and college roommate a lecture. He gave him a lecture because I was skipping class so much.
Oh, man.
So this proof here was actually solved in two slightly different ways by Aristotle, but each follows the same basic strategy, which is actually pretty similar to the human solutions out there. So if you look and you can see all the comments, you'll be able to follow this one pretty easily. And by the way, this proof made extensive use of test time training. Basically, we trained on the fly using proof explorations of this problem, which is a pretty awesome technology. It's also the longest proof we generated, clocking in at about 1,500 lines of lean code, which would have taken me probably 6.5 weeks to formalize by hand.
At least.
That's amazing. Let's move on to P5, which is another combinatorics problem. They seem to have liked those this year.
Right. And this one's interesting because it's a game problem.
Yeah.
A lot of the others had a kind of a visual flavor, but games are kind of similar in a weird way because people have a lot of intuitive notions about how games work, right? You know that all of the players are trying to win. You know what it means to win or lose a game, and so on.
Can you say the names of the players?
That's right.
To make sure that the audience understands.
So we're talking about Alice and Baza.
Alice and Buzza.
And they're playing the
I wish I had a friend named Baza.
And they're playing the inequality game, spelled with a koala in the
Very
middle
Australian,
there.
very on brand.
And our model actually found this problem very difficult, but we did solve it. And the proof is shorter than I would have expected for a game problem. I should mention that the proofs that many of the proofs that people are talking about on the forums involve a lot of case analysis. But this proof is very direct, which I think is maybe why it took so long to find. Despite being shorter, it's kind of more rare or special. And kind of the key insight for this problem, these definitions are just sort of the setup, but the key insight is to define what the model calls these reference strategies, which actually turn out to be the optimal strategies for the players. So the proof proceeds by just sort of defining these up front, again, probably from a process of trial and error, and then proving a whole bunch of lemmas that talk about the behavior of the reference strategies. So talking about, maybe on this turn, this player wins after some point, something like that. And then it closes out the main theorem with an unusually long sort of final main proof. And again, lots of more interesting details that I'm skipping over, but I think game problems are fun.
And these types of problems are notoriously difficult to express formally, usually, right?
That's right. Yeah, that's why I'm surprised that the final proof isn't many thousands of lines.
It's amazing. And what about Q6?
We did not solve problem 6 this year. No other AI system did, although many of the human competitors, maybe I shouldn't say many, some very, very bright high schoolers did. I think one reason that maybe we didn't is that the solution to the problem was actually printed on the floor of the airport near the competition. So we did not travel to the competition,
Let's
and
show
Aristotle
that.
Didn't look at the floor.
I think we have, so that's the combinatorial, actually the construction.
Right.
This is the new benchmark for mathematical
Yes.
reasoning.
And there's the
floor.
the floor of the Sunshine Coast Airport. So I think that's why it was difficult for the AIs. They didn't actually travel to the Gold Coast to solve this problem.
Maybe next year.
Cool. Well, thank you, Aiden. Amazing work. And by the way, I should also add that some of the students and mathematicians working with us have already used Aristotle to accelerate their research and their formalization work, as well as make contributions to MathLib, which is Lean's standard mathematics library, sort of like a repository of all mathematical knowledge.
Yeah, and to that point, these IMO proofs are now live on our GitHub, right here at this link, so feel free to dive in and experience them yourself.
The amazing thing, I think, about going through this competition and cranking on these problems, besides the great camaraderie exhibited by the team, is that we actually unearthed so many ways that we can improve not just the AI, but also the interface to it. So wanted to give you a little bit of a preview on some of the things we're building next. So number one, a smarter model, perhaps an obvious one, but the model continuously gets bigger, smarter, and not only that, but we already have plans to give you verified hallucination-free answers to questions not just in mathematics, but all downstream domains where verification is useful, like physics and coding, software engineering. Number two, multimodality, and this includes automatic diagram generation, particularly useful for geometry, as you showed, and topology, but also for things like Feynman diagrams for our physics friends. Number three, advanced voice mode. So why don't we talk a little bit about this one? Tudor, have you ever had the experience of hanging out with your buddy late at night, smoking a tobacco pipe, talking about math?
Weird enough, that happens all the time.
You love it, don't you? Well, so did Einstein and his buddy Gödel. So, well, here's the problem. Not every mathematician has a buddy available. Some of us can be quite introverted. So we wanted to bring that experience to you. So your mathematically super intelligent companion by your side, whether you're going out for a stroll or hanging out next to your chalkboard like Professor Einstein here.
Sounds great, but Vlad?
Yes?
Well, we've talked a lot about what's going to happen in the future. What's available right now?
Well, funny you should ask, because one of the things we're really excited about is this being the first advanced mathematical reasoning model that's actually usable. Now, one of the core values of Harmonic from the very beginning has been to make mathematical superintelligence broadly available, not just to large corporations, but to everyone, in forms that real people can use and benefit from.
Well, if that's the case, why don't we just let people start using it today?
Let's do it. So, without further ado, introducing Aristotle for iOS. So, if we can get up my iPhone display here, I can tell you a little bit about what we've got. All right, the first thing you notice here is the logo, which actually, as a design nerd, as you know, I get pretty excited about. It's an abstract eye shape that incorporates a thunderbolt at its core. It's meant to evoke vision and intelligence, but also the thunderbolt adds speed, power, and the sudden clarity that comes from a brilliant insight or a spark of genius, very important in mathematics. Together, they also resemble the planet Saturn, which is one of my favorites, but is also once thought to be the furthest planet and the limit of our known universe. So let's tap to open the app. Now, if I go to the home screen here, you'll see that there are 3 ways to submit a question. You can type it in, take a photo that has some math on it, or upload an existing photo. So what I'm going to do, I think this is a little bit of a unique feature, so I'll show it to you. I'm going to upload a photo. I'm going to take a photo of this chalkboard and process that. So, and actually I'm a little nervous about this because the Wi-Fi in this garage has been pretty flaky all day. So hopefully it gets there. But one of the problems with math solvers in the past has been typing in symbols. It's annoying and super cumbersome. Now, what we're calling PhotoSolve removes that pain point. And the AI has basically gotten so good that it just works. So
you can take photos of multiple problems and it'll just do it?
I mean, if you look at these problems here, this has complex symbols. It has infinity, it has open-close brackets. You can see there that I have a geometry problem with chicken scratch.
My favorite.
And number 4, of course, the Riemann hypothesis. So I'll go ahead and deep solve them. And deep solve is very interesting. So you can actually see, I took a photo of the left two problems here of the chalkboard. And it got the symbols right, and it's cranking through the proofs. And it extracted them even though everything on the chalkboard was handwritten. So you can solve in a batch, which is what I did, or you can also solve one at a time. Deep Solve, what I selected, actually makes use of our formal verification technology. So let me actually tap into it. So you can see Aristotle is cranking and actually proving the question. You have this slider here at the top, which lets you transition from the English to the lean. So in this case, it defaults to English. But I should say the English translation from lean is still imperfect. So you can always go to lean, which I would consider to be the source. And there you can see the precise machine translation of this problem. And by the way, this is like a non-trivial real analysis problem.
Oh, wow.
You know, this is like in my P set at Stanford, I would have probably spent 3 or 4 hours on this. So there's that one. And let's see what this one's doing. So this is another real analysis problem. Suppose f is a continuous function, and we have to prove that it's uniformly continuous. So I can tap, and I can see that it's been auto-formalized, and it's continuing to crank on it. Now, likely what's happened is it's proved it, but because of the connection, the proof might have not made its way here. Now, one thing that we do is you can see in my questions here, you have your history. So you can see it didn't successfully prove the Riemann hypothesis.
Really?
No.
I think we're close, though. I think we're close.
But if you look at what this looks like when it's fully proved, you can see we extract lemmas from each problem. So basically, that's Aristotle decomposing the problem into small problems, proving those. Each one of them is formally verified, and you can, of course, see the lean as well as the English by tapping the switcher. And if you background the app, basically what you can do is you'll get a push notification once this proof is complete, and you can just like go right to it. So main differentiator, you can see the lean, you can see that there's verification, and that should give you high confidence in the reliability of the solution. So yeah, I showed you the lemmas here. I think those are very cool. And yeah, how amazing is that?
It's crazy. And how do we explain, how is it different than a ChatGPT or Claude or Gemini?
One word, verification, built in as a first-class primitive. So Aristotle is the first product that we know of that combines the expressiveness of an LLM with the airtight verifiability of a graphing calculator. In other words, no hallucinations. Aristotle will only give you an answer when it's absolutely sure that it's right. And when it's not absolutely sure, it'll tell you that also. I think this will make it an indispensable tool, not just for students, but also the professional world. Now, we're going to be opening up early access to Aristotle today to our very first group of users. So if you want to be one of them, the waitlist is live right now at harmonic.fun or at this QR code here that you see. Now, this is going to be a cross-platform product with iOS available first, literally today, and then Android web as well as direct API access following closely behind. In the coming months, we're also going to be adding a new mode, which I'm very excited about. We're calling it IMO Gold mode, okay? And you can imagine that this will be very, very powerful. It'll let you solve the most difficult mathematical problems.
This is super exciting. You know, these problems caused me hours of pain in college, and it's been amazing to see Aristotle crank through them in a minute. Should we take some of your questions now?
All right, let's see what you guys got. All right. Do we have any questions? I think we do have some. Oh God, my questions aren't loading because of the internet. Okay, here we go. All right. How amazing is that? Okay, question number 1, David Fow. Okay, I know David Fow. Where does Vlad Tenev get his suspenders? A real heavy, hard-hitting question, David. Thank you for that. I believe these are from Amazon, actually. Yes, you might be surprised. You thought I would be wearing some designer shit, but no, Amazon it is. Okay, let's move on. Here's a harder one.
Okay.
From Sarah on Twitter. How long did the run for each problem take?
Yeah, some of the runs solved within time. Some of them took a little longer. You know, the way the Aristotle system works is it's running a lot of proof searches in parallel. And those proof searches, because they're happening in parallel, they kind of reinforce each other. And then we have to build on that over time. So, you know, the system can run for like quite a bit before solving a problem. But the thing is that, you know, with the self-improving nature of reinforcement learning with this formal feedback, if you hold the difficulty level constant, the time to solve just decreases every single week. So, you know, in the near future, we actually anticipate solving these problems very quickly and regularly.
Yeah, and I should also add that I think it's a little bit of a misnomer to talk about the time that each problem has taken to solve, because really the question is how much compute, how many flops of compute. And you know, when AI labs are talking about the time, it's because they don't really want to talk about the compute, because I think that's viewed as somewhat sensitive. I mean, we may talk about it in the future, but I guess not quite at this point. Okay, one more. This is an interesting one. I don't know if we have a good answer, but we'll try. Looking at the attempts for Q6, what was the bottleneck? What could have been done differently to increase odds of solving it? What do you think?
That's an interesting one. You know, I think our system actually did make quite some progress on it. We are interested in fully formally verified solutions. So that means that, you know, we weren't really interested in submitting for partial credit. I think that as MathLib, which is the core math library for Lean, expands, I think solving questions like some of these certainly gets a bit easier. But you know, I think in the coming months that's going to happen, especially with Aristotle's help. And you know, I certainly think some of these bottlenecks, at least for Q6, are going to be resolved pretty soon.
Yeah, and I think actually that there's sort of like two interesting things about this problem, question 6. One is you have to notice that 2025 is a perfect square. It's like 45 squared, which I believe our system did notice. Then you have to like try some smaller constructions, again with perfect square boards that are smaller in dimension, and kind of extrapolate that visually the same pattern would hold. So I think the AI models will get there.
Yeah, also the multimodality is going to be important for that. I think like for that sunny lines problem and also for Q6, as Aristotle becomes multimodal, I think that also gets a lot easier. Yeah, that's another good point.
Okay, cool. Let me ask one question, one more. Maybe we cut it off at one more. Did Aristotle have access to any libraries for this with either theorems or definitions? And what were the imports at the top of each file? I think we actually showed those, but...
Yeah, you'll be able to see it. So we use MathLib. We also have an internal package that we ran with, but basically it's essentially just MathLib. Our internal packages bring a couple other things into the SIMP system, if you know what that is.
Okay, sounds good. Let's see. And actually, how about one more question for you? What do you think, how do you know that this is gold medal level performance? Was this graded or verified by mathematicians in some way? Was it like...
Yeah, no, so
was it scored?
That's the thing. So, you know, with our system, you know, you are able to have the computer verify the proof line by line, and it's completely airtight. So when our system output the proof, nobody has to look at it. You know it's correct. And that's the experience we hope users will have on the Aristotle app as well.
Couldn't said it better myself. All right, so shall we wrap up the questions and close out? Let me say, we have a vision of the world where you can indeed snap a photo of the Riemann hypothesis on your phone, and our system will solve it and create a formally verified proof. And I think it'll either be Aristotle or one of his descendants. I don't think any other company, actually, at least that I know of, is singularly focused on this goal.
Yeah, and you know, we have an amazing team, and as we scale up Aristotle, scale up MSI, we're looking for amazing people to join us. So If you're interested in this kind of work and pushing the frontiers of mathematical reasoning, check out the careers page at harmonic.fun, and we'd love to work with you.
Yeah, and we'd like to end the live stream by acknowledging the great mathematicians that came before us. Bernard Riemann, Bertrand Russell, Georg Cantor, Kurt Gödel, and of course the mathematician that I went to UCLA to study under when I was quite a bit younger, Terence Tao. And we stand on the shoulders of these and many other giants as we pursue mathematical superintelligence. I think this may be humanity's ultimate discovery, ultimate mathematical discovery. We believe that with the appropriate guidance, it'll help generate a large portion of the useful mathematical theorems and proofs in the future, and consequently contribute to the fundamental discoveries in physics and all downstream fields.
Thanks so much for joining us. I hope you can see that the team has poured their souls into Aristotle, and as with any harmonic product, you can expect that it'll recursively improve at an accelerating rate once it's in your hands. Enjoy it, and see you soon.